Hey everyone, so I said we would pick up here on the quick check that was assigned page 177. So if you have not attempted these questions, you should give it a go. I strongly recommend reading page 175 and 176. So when I look at the labs and just marking the labs, still quite a few of us struggling with formula writing and identifying the charges, etc. So this is really important, and I suggest you read 175, 176. Have a look at the terminology there, net ionic, complete ionic, spectator, and so on. Okay, the first questions that I asked were 1A, C, and E. And here it wants you to just write the formula of the precipitate that forms. So we want to look at these as just double replacement reactions. And so we're essentially swapping partners, right? But you have to be really careful when you swap partners because whatever the ratio is between the elements barium and sulfur here is not necessarily going to be the same as the ratio between, so when barium switches places with magnesium, right? We need to make sure we understand that barium is +2 and sulfate is -2. And so we have to build the compound based on the charges of the ions, not based on the subscripts that we would see in the formula, right? So in this case, the double replacement reaction, barium's +2, sulfate's -2, so they're going to get together in a 1-to-1, and you're going to get barium sulfate. And then we simply look at the alternate, which is magnesium and sulfur, which gives us magnesium sulfide. And again, magnesium in this case is +2, sulfur's -2. So they do happen to get together in a 1-to-1 ratio, right? So once you've decided, sorted out the double replacement, then it's a matter of going to the table of common ions and sorting out which one has the low solubility. So if you've checked out that, you would see that sulfate has a low solubility with barium. So this would be your precipitate and everything else would be aqueous, right? These would be aqueous as well, but it didn't indicate that, although it says mixing the solutions, right? So if you look at C, again, double replacement, here we'll see the difference in the formula writing. So the H is our positive ion, which is going to replace our zinc, and we're going to end up with hydrochloric acid, HCl. H is +1, chloride is -1, so they get together in a 1-to-1 ratio, and that's going to leave us with zinc phosphate, and it's going to be zinc 3 and brackets PO4 with a 2. And if we look this up, well, we're familiar with hydrochloric acid. We should know an acid such as that is very soluble. So this is our precipitate, and so we would have solid there. So we've got barium sulfate being our precipitate in the first one, zinc phosphate precipitate in the next one. And for E, we've got manganese iodide and strontium hydroxide. This is going to give us manganese hydroxide and strontium iodide. And in this case, our precipitate will be the manganese hydroxide. And so this would be solid. All right, so that's identifying your precipitate in the double replacement reaction. The next question is now getting you to, once again, go through writing the double replacement. So from the double replacement to the complete ionic to then the net ionic by identifying spectator ions. So here's our reactants, magnesium sulfide and zinc chloride, which is going to give us zinc sulfide plus magnesium chloride. Before we proceed any further, we want to identify the precipitate here. So again, we got to go to our table of common ions and solubility of compounds. And we recognize that zinc combined with sulfur has a low solubility. So this is our precipitate. Everything else is aqueous. So we need to identify that to then go to our complete ionic equation. So our complete ionic equation, everything that's aqueous should be written out as its ions, Mg2 plus S2 minus. Oh, just to make sure that we are balanced, right? This one was pretty straightforward because magnesium 1, sulfur 1, zinc 1, and chlorine has 2. So it's already balanced. So we've just got plus Zn 2 plus 2 Cl minus. These would all be aqueous. So we want to make sure that we write that. And then we've got on this side, the zinc solid precipitate stays as solid, and the magnesium exists as its ions in solution. So we go through canceling out. That's our complete complete ionic equation. We go through canceling out our spectator ions. So if it appears on this side, in the same way as it is on this side, they cancel out. The chloride cancels out, and we're left with what would be the net ionic equation. And that net ionic would be S2 minus plus Zn2 plus as aqueous going to ZnS. And that's the net ionic. All right. Going back to our PowerPoint. So we've looked at a lot of double replacement reactions. And so what I wanted to just go through here is to show that we can have the same thing happening with a single replacement. And remember, single replacement can involve both metal ions, so like a positive ion replacing a positive ion, or a negative ion replacing a negative ion. What I want you to make sure you understand in the case of a non-metal replacing a non-metal is most non-metals exist, like say fluorine, for example. They're molecular compounds, right? So fluorine gas, and I really did notice this on the lab, that we're really not recognizing the nature of certain substances based on our previous experience. It might be just so long that it's been for some of you with respect to chemistry, but fluorine gas exists as a diatomic molecule. It's molecular, right? So in this single replacement reaction, we've got fluorine gas bubbled through a solution of sodium chloride. This would be our balanced molecular formula. Now notice F2 as a gas. It's bubbled into a solution, aqueous, of sodium chloride. And we're going to get a single replacement in which fluorine is going to replace chlorine. In this case, kicking out the chlorine is going to leave us with chlorine as a diatomic molecule in a gaseous form, and we're going to end up with sodium fluoride. All right, so that's the balanced molecular formula equation for the single replacement. And then what we want to consider is total ionic. Okay, so when we separate things, this does not separate. It's a molecular compound, right? And so I'm seeing lots of students, like on the lab, for example, when we had a situation like sulfur dioxide as a gas, and I was asking to write the dissolving of this gas in solution. Well, it would stay as sulfur dioxide, and simply the state would change. It's a molecular compound. It doesn't dissociate into ions. So the same way this fluorine doesn't dissociate, but the sodium chloride is an aqueous solution and it separates into its ions. On the opposite side, on the product side, we have chlorine gas that stays as chlorine gas, Cl2, doesn't separate. But the other compound, sodium fluoride, does separate into its ions. So this is our total ionic equation. If we cancel the spectator ions, sodium cancels with sodium, and that's it, right? Because these other substances remain behind, and that gives us a net ionic equation of the following: fluorine gas plus 2 chloride ions. Again, I'm seeing lots of equations written without the appropriate charges. And this is enough students where I'm not seeing people coming and asking questions and asking for help. And I should be, right, at this point. So again, the fluoride ions have the charge. All right. So some things to pay attention to, and we talked about this last week. Sometimes you'll have a situation in which there are no spectator species. So then the total and the net are the same, right? So if we back up here, if you had a situation in which there were no spectator ions, the total ionic equation would be the same as the net ionic. Um, Occasionally, all species in the total ionic equation are spectators. Everything cancels out, right? What does this mean? It means that everything is soluble, right? And so that there's no reaction forming a precipitate, and the ions simply exist in solution as one big happy family. We talked about this last week, in which these copper, the difference between copper plus and copper 2 plus. And so copper plus 1 has a low solubility with the halogens being fluorine, chlorine, bromine, iodine, right? And so when you look these up, you have to be really careful of the formula. So if I'm looking at this versus this, and if you just go and look up copper on the table without paying attention to what, oh, sorry, copper iodide with a 2, this is copper 1 iodide, whereas this is copper 2 iodide. And the difference in that is that this is copper plus 1 and this is copper plus 2. This has very low solubility. This does not. This is very soluble. Okay, so we've got to pay attention to those little things. You've got to be able to use charges of ions, sorry, you must be able to use the charges of ions in the table to write appropriate formula for any precipitate that forms. And I think some of us still need some refresher on those. So if you can come to see me for some help. We've gone through how to be using the table. So what we're talking about here is in the second half of 3.2. Okay, I'm just going to flash ahead here. So you can't see this. So I'm going to try and slide this up. Hoping. Let's have a look here. Okay, just adjusted the screen there, so hopefully you're seeing that now. But we're talking about selective precipitation. Whoops, my pen stopped working now. Selective precipitation. So this starts on page 177 in your book, and it's talking about qualitative analysis. And so here we're looking at a procedure that can be used to help identify unknown solutions or unknown ions in a solution. So selective precipitation, identifying unknown ions in solution. Okay, so we talked a little bit about this already, but so let's say you want to know if a solution contains silver ions or strontium ions. Okay, and so you would have to perform an experiment in which you add a certain soluble substance to look for a precipitate. So you're looking to add a soluble salt of a specific type, right? Maybe I'll write this down here. Okay, sorry, I paused the video and I wrote it out. So if you look down in the bottom here, this process, all right, we're trying to identify if a solution contains silver ions or strontium ions. There's a couple different ways to do this. You can do it in the form of a table, or you could do it in the form of a flow chart, which your book shows you on page 179. And again, we'll hopefully practice with this a bit on Monday, but so let's think about this. You want to add a soluble salt of a specific type that would precipitate one of your ions, silver or strontium, but not both, right? So if I was unaware that I had silver or strontium, or I knew I had one or the other. So I could add sodium chloride. Now, the reason why I would add sodium chloride is sodium is an alkali metal. It's soluble with everything. So what it ensures is that I've got chloride ions in solution. Then I look on my chart. The reason why I'm picking sodium chloride is if I look on my chart, silver is low solubility with chloride, a precipitate would form, but a precipitate would not form with strontium. So if I ended up with a precipitate, I could be sure that the substance I have in my solution is silver, not strontium, because of the fact that if I added sodium chloride, the chloride would react with the silver and give a precipitate. Okay? I wouldn't want to say pick sodium sulfate because in this situation, both things would precipitate, and a lot of precipitates tend to be the similar color, like white powders. So we wouldn't know whether the precipitate is one substance or another. It wouldn't clearly identify. Another possibility, and I'm using sodium because sodium is an alkali metal and it's soluble with everything. You could add sodium sulfide. Again, you would get a precipitate with the silver if it was silver. If the solution contained strontium, you would get no precipitate. But the fact that you got a precipitate or didn't would tell you which solution or which ion is present in the solution. So all in all, when we look at this chart, we're seeing that there are a number of different things that we could add: sodium chloride, sodium sulfide, sodium hydroxide. Of course, I could pick potassium hydroxide or lithium hydroxide. All of those alkali metals are soluble, form soluble compounds. And in this case, any one of those, sodium phosphate, would give a precipitate with silver. All right. So make a chart. Or like I say, make a table or use a flow chart when you are doing these things, identifying whether precipitates form or not. So how would you identify silver, barium, or nickel in a solution? What ions would you use and in what order? So let's say, for example, you wanted to isolate the ions. Like I've got a mixture that contains silver, barium, excuse me, sorry, and nickel. So I've got a solution that contains a mixture of all of these, and maybe I want to separate them. So you can see here, there could be an order. I could add some sodium chloride. The chloride would combine with silver and form a solid silver chloride precipitate, and then I could filter that. I could filter that solid precipitate, removing it out of the solution. Then I could tackle the barium, and the order is important. I could tackle precipitating the barium by adding, let's say, potassium sulfate. Potassium sulfate, the sulfate would form a precipitate with barium. All right. That would form a solid in the solution, and then I could filter it, just like you filter your coffee. You put a little filter paper, pour your solution over top, the aqueous stuff's going to go through, and the solid stuff's going to remain behind in your filter, so you've isolated the barium sulfate. And then you would just have a solution left with nickel, and in this case, you could use sodium sulfide. It wouldn't matter to use sodium sulfide because you've already removed the silver. You wouldn't want to start with sodium sulfide first because you would precipitate both silver and nickel at the same time, and I'm not sure how you would get those little tiny grains apart once you filtered it. So you wouldn't want to start with it first. But now that the silver's already gone, adding sodium sulfide would cause a precipitate with the nickel, and then and I think it's nickel +1, so this would look like this, nickel Ni2, and then you would filter that. Okay. We will look at some more questions of this on Monday and do some examples and such together, but I strongly encourage you to make sure you read page 177 to 179. And I will post a second video for 3.3, hopefully by the end of the weekend.